Hi guys, in this section we're going to be studying an application of integrals. In particular, we're going to be looking at areas between curves. So what do I mean by that? Let me do an example to start us off. Areas between curves. So let's try to find out the area between f of x equals 2x and g of x equals x squared minus 4x. Well, if I want the area between these guys and I have no clue how to do this, maybe a good way to start would be to graph the two functions to see what I'm actually up against. So let's take a look at the graph. So I know that f of x equals 2x is just a line that goes through the origin. It's got a slope of 2, so maybe it looks something like that. And this guy is just a quadratic function. So if I factor it, then I could see that this guy will cross the x-axis at x equals 0 and x equals 4. Let's say this is 4. I also know that this guy is right side up. So it'll be a u. So let me fill this in. This tells me that the region that I'm actually interested in is this stuff here. All right, well, how do we do this? What we're going to do is we're going to think back to the beginning of the quarter. And we're going to think back to how we actually thought about area when we were approximating it. And what we did is we thought about drawing rectangles. So let me actually draw some rectangles in this region to see if we might be able to then figure out what integral might be helpful. So in particular, if I'm going to start approximating, let me just draw a couple of rectangles. They might look something like this. And what I'd like to do, if I call this guy f of x and this guy g of x, what I'd like to do is I'd like to approximate. This area. And if I look at a given rectangle, it's going to have width delta x and height. Well, let's see. If I take this distance, that's just f of x sub I. And then I just need to add this distance. So we have to think about this. Our g of x function down here happens to be below the x-axis. So the functional values are negative. So if I actually want the total distance, I'll take this positive value, f of x sub I, and to that I will have to, again, add this distance, but since the g of x's are all negative, one way I could do that is just subtract g of x sub I. So I have a positive value minus a negative value, which is then adding in that as a distance. If I then take the limit as n goes to infinity, that will give me the area between the two curves. Well, in integral form, this is just the integral from 0 to 4 of f of x minus g of x dx. In other words, we have the integral from 0 to 4 of 2x minus x squared minus 4x dx. And I'll let you guys actually work out that particular integral. All right, so it looks like what I'll be able to do then to find the area between these two curves is just take the top minus the bottom. So this looks like top minus bottom. Okay, as a more interesting example, I'm going to try to find a different area. let's try to find the area between, find the area between y equals sine of x, y equals cosine of x, x equals 0, and x equals pi over 2. So with all of these types of problems, what you want to do is really sketch this first and try to determine what your region is that you're trying to find the area of. So I'm going to give you a minute. I would recommend pausing the video and trying to come up with the region and just draw some rectangles. Right, hopefully you gave that a shot. Well, let's see. Pi over 2 is here. Then sine of 0 is just 1. And the sine function, as I go from 0 to pi over 2, that will, cosine function. Cosine of 0 is 1. As I go from 0 to pi over 2, the cosine function, which spits out the x coordinates. So I move this way to pi over 2. The x coordinates are getting smaller and smaller. So the cosine function is going to look like this. The sine function, sine of 0 is 0. We're spitting out the y coordinates. And as I move from 0 to pi over 2, the y coordinates are getting bigger and bigger. So my picture is going to look like this. So this is sine of x, and this guy is cosine of x. Okay, the area between y equals sine, y equals cosine, x equals 0. So that'll be this line. So let's see, I guess this will be one of the bound regions. And x equals pi over 2. So x equals pi over 2 is this guy, so this would be the other bound region. So if I extended this line, the problem is that nothing is bound over here, so that's why I don't include it. So typical rectangles are going to look like this. Maybe this guy, and maybe this guy over here. So at this point, I want you to stop the video and ask yourself, why is this problem any different than the previous problem? Well, hopefully you said that in this problem, it looks like my top and bottom switch from 0 to this intersecting point. Cosine is on top, sine is on bottom. And then from here to here, sine is on top and cosine is on bottom. Well, how do we handle that? What we need to do is first find that point of intersection. We need to know where sine of x is equal to cosine of x. And one way you can do this is divide both sides by cosine. If I divide both sides by cosine, I get tangent of x equals 1. And arctangent of 1 is just going to be pi over 4. Or another way you can think about it is we want to find the radiant angle where the y-coordinate equals the x-coordinate. In other words, where we're on the line y equals x on our circle. And that's, once again, at 45 degrees or pi over 4. So this guy's pi over 4 here. And again, I want to find these rectangles here and then these rectangles here. So I'm going to have two integrals. I'm going to integrate from 0 to pi over 4, and we'll fill in the details in a second, plus integrating from pi over 4 to pi over 2. So that'll be a different setup. So once again, I want to get the height of the ith rectangle. Its width is delta x. And when we construct the limit and convert it to an integral, it'll look like this. That'll be our quote-unquote dx. So what's the height of this guy? Well, the height of this guy is going to be this distance, which is given by cosine of x, minus this distance, which is given by sine of x. So this integral is going to be cosine of x minus sine of x. Analogously, if I want to find the height of this rectangle, I can take this distance, which is sine of x, and subtract this distance, which is cosine of x. So we therefore have sine of x minus cosine of x. Once again, let me note that we have top minus bottom, but our tops and bottoms are changing through this process. So that's another problem, a little bit more interesting than the first. And now let's look at a problem that's even more interesting. I'm going to call this one even more interesting. So here's the example I have in mind. So I'd like to find the area between y equals x minus 1 and y squared equals 2x plus 6. So again, my suggestion with all of these problems is to first sketch the region so you know what you're actually up against. Let's take a look at this guy. And one thing that you may have never sketched before is a y squared function. So I'm sure you guys are super familiar with y equals x squared, et cetera, or in general y equals ax squared plus bx plus c. But now we're looking at a y squared function. Well, let's start thinking about this. There are a couple ways you can think about it. One is that if I have a y equals x squared, then it's going to look like this. In other words, all of the y values are going to be non-negative. If I just had x equals y squared, then analogously the x's are going to be positive. So one way that I can think about this is to solve for x. So in other words, y squared minus 6 equals 2x. Or dividing both sides by 2, we get that x equals 1/2 y squared minus 3. And what I can do is I could think about this as the y squared function scaled by a half. So the y squared function scaled by a half, and then shifted left by 3, because we're going to subtract the x values. So in doing so, let me put minus 3 here, and just draw this guy. Let me say that another way you could have thought about that is y is equal to plus or minus the square root of 2x plus 6. So what that's telling me is that the positive square root of 2x plus 6 is this guy up here. So everybody hopefully knows what a square root function looks like. And then if you plug in x equals minus 3 here, that's where the 0 is. So that's where it's shifted back to. That's why that's minus 3. And then the negative version is going to be the minus square root of 2x plus 6. So either way, you can think about it. We then want to sketch y equals x minus 1. So before I sketch that, I want to get a sense as to where these guys intersect. In fact, that'll help me with the sketch because I think it's going to bump into it in 2 places. And if I can find those 2 points, then I could just connect those and have a pretty accurate picture. So how am I going to find out where these 2 guys intersect? Well, in general, whenever you want to find out where 2 functions intersect is you set them equal to each other. So in particular, I've got y squared equals 2x plus 6. So I could say, okay, I guess 2x plus 6 is going to equal x minus 1 squared. That will give me the x coordinate where those 2 guys intersect. So in other words, 2x plus 6 equals x squared minus 2x plus 1. I just expanded that. I could then bring everybody to one side. So let's see, x squared minus 2x is minus 4x. 1 minus 6 is minus 5. And it looks like x minus 5 and x plus 1 will do the trick. So x equals -1 and 5. Those are the 2 points where this guy is going to intersect. So -1 and 5. We call this 5. So it's going to look something like this. All right, so a bit of work to get the region that we're interested in. At this point, I want you to stop the video for a second and ask yourself, what's more challenging about this example? How is this one different than the ones that we've looked at? All right, well, hopefully you said that, well, this one's different because, well, first off, here's my whole region. The top and the bottom are changing. Not only that, but the top is part of this function. I guess the top part, and we're sticking with the same function, looking at the bottom part, and then it switches over here. So there's a lot more going on here. So let's see if we can figure out how to solve that. There are actually 2 ways. Let me draw my rectangles, though, so that I can get a feeling as to what's going on. So that would be a typical rectangle on that side, and that would be a typical rectangle on that side over there. So first off, it looks like my top and bottom change at this point, and we already saw that this point was where x is equal to -1. So I'm going to integrate from -3 to -1 something, and again, I'll fill in the details in a second. And then from -1 to 5, that'll be a different integral. And I'll take care of that in a second as well. So if I think of this guy as a function of x, that'll give me this height. And if I think of this guy as a function of x, that'll give me this height. So we already talked about the fact that we could think of this as the square root of 2x plus 6 on top and minus the square root of 2x plus 6 on bottom. So in other words, you could just take this distance, which is the square root of 2x plus 6, minus the square root of 2x plus 6. So again, why am I subtracting? Why am I doing the top minus bottom? Because this functional value is negative, and I want to actually get a distance. So if I didn't have that there, the double negative, then I wouldn't actually get the total distance because I'd be subtracting out this piece. And in fact, the astute student out there might realize, well, wait a minute, this is just twice the square root of 2x plus 6. And that makes sense to me because this quadratic is symmetric about the axis. All right, that's that piece. And what about the second piece? So once again, I just need to get my height of the ith rectangle. So I could just take this distance and subtract this distance. So the top distance is going to be the square root of 2x plus 6. And then the bottom distance for a given x is just going to be x minus 1. So that's how you would set up that integral. Well, that was a lot of work. This is a lot of work, and this is it'll still be a bunch of work to actually integrate that out. So I'm wondering if there's a better way. And in fact, there is a better way than top minus bottom. Let me erase some of this and revisit the problem, thinking about it differently. So up until now, we have been integrating with respect to x. So in other words, our delta x's are this way and our f of x's are this way. Well, what we're going to do now is we're going to turn our head sideways and we're going to think about this moving this way. In other words, we're going to be integrating with respect to y. So what would a typical rectangle look like in this case? It would look just like that. So if you stack a bunch of these guys and stack more and more of them, then as you take the limit as n goes to infinity, you'll get an integral. So let's actually go through that process. Well, in the approximate sense, if I have n subintervals, the ith subinterval is going to have a rectangle of width, no longer delta x, but now delta y. Put that out here. And then I need the height, or the length of the ith rectangle. Well, for a given y, all I need to do is take this length, and let me call that f of y sub I. And then I can subtract this length from here to here. So the distance from here to here is going to be g of y sub I. So let me call this guy f of y. Let me call this guy g of y. So again, what I'm doing is I'm going up to a particular y value. I'm taking this distance, and then I want to add this distance. But if I want to add this distance, since my g function is negative over here, I really have to subtract the two, because subtracting the negative number will be analogous to adding it. So this is an approximation, and I'll take the limit as n goes to infinity. Well, what will our integral look like? Will it look like this? No, it's going to look like something very different. It's going to be in terms of y values. So again, I'm now thinking, instead of from here to here, I'm thinking of adding up the rectangles this way. So where are my y values going from, and where are they going to? Well, the x values, again, we're going from -3 to 5. The y values go from this y value up to whatever the heck this y value is. And I can get those values just by plugging them into my functions. So in other words, when x is -1, y is equal to -2. When x is equal to 5, 5 minus 1 is 4, so my y is 4. Then I want to take this guy as a function of y. So in other words, if y equals x minus 1, then y plus 1 is my x value. So for a given y, if I want this length, if I want that x, then for that given y, I need to use y plus 1. Y plus 1 will spit out the associated x value. Similarly, I'm going to subtract this guy now in terms of y's. So in other words, y squared, again, we did this a minute ago, -6/2 is going to equal x. I'm going to subtract y squared -6/2. And the reason, again, that I'm subtracting it is what that'll do is that will give me the opposite of that x value, which makes it a positive value. So what I'm doing is I'm adding these two guys together to give me the length of the ith rectangle. Now, small typo here. That should be dy. All right, so looking at this, then instead of thinking top minus bottom, when I'm integrating with respect to y, I'm going to be thinking right minus left. And I'm going to do that when I realize that it's an easier process for me to integrate than having to break it up into multiple regions. So I'd like to give you guys one more example for you to try on your own. Stop the video, give it a shot. I just want you to set up the integral. And let's see if this process makes sense to you. So in this final example, I'm going to draw the picture for you. And then have you guys try to set up an integral corresponding to the associated area. So, let's see, this guy is y squared equals x. Sorry, I wanted to put this a little bit further in. All right, so the region that I'm interested in is this guy here. And let me point out that if you did this with respect to x, this would be a pretty challenging problem because you'd have this top minus this bottom. That would take care of this area here. Then this top minus this bottom, again in terms of x's. Then this top minus this bottom. So it would be a lot of work with respect to x. So pause the video and let's see if you can set up the integral in terms of it being right minus left. So hopefully what you did is you first drew some rectangles to get an idea as to what these guys look like. So typical rectangles might look like this or this. Again, I'm going to look this way. So I can see that the width of a given rectangle is delta y, and that will translate to dy in my integral. Further, it's just going to be one integral because the right minus left never changes. It's always this function over here, and then this guy on this side. My y values go from -1 to 2. And then I need to get, once again, the ith length of this guy. So it's going to be this distance for a given y. Well, for a given y, I want this distance. So if I plug in my y here and square it, I'll get that distance. So that'll be y squared. Then I want to add this distance. But again, adding that distance, since the x values are negative on that side, what I want to do is subtract out the particular x for that given y. So if I subtract out y minus 5, then since this number itself is negative, by subtracting it out, it's like I'm adding that value back, and that's giving me the length of the total rectangle. So that's how you find areas between two curves using calculus. The main takeaways are that you definitely want to draw this thing. Your problem is either going to be top minus bottom, or it's going to be right minus left, and your picture is going to tell you the best approach. So I hope you enjoyed this video, and thanks so much for listening.